Okay, we're in the 4.2 packet. Okay. I'm going to look at page 21. Okay, number one says find the sum. So finding the sum, we're just going to do this by hand. Right? So we start with the lower bound, and we're just going to enter 2 in for all the i's. And after we're done with 2, then we're going to move up to 3. And then finally, we're going to end with 4 because 4 is the upper bound. And we're going to add all the terms together. Okay. So we're done with 2. Now we're moving up to 3. End with 4. Get 3 squared, which is 9. Root of 16 minus a negative 1. 25. And then 2 cubed is negative 8. Okay, add those terms together. 59. Okay, so now number 2, we're going the other direction. Use sigma notation to write the sums. Now we want to try to get these sums to be in this form. Okay. So typically, what we can do is we can do summation. Basically, what needs to happen is I need to be able to insert I equals 1 into some pattern to produce this. Then I'm going to plug I equals 2. Then the next term will be 2. 2 has to plug into this to get that. 3 will insert into some expression to get that, and then 4 will insert into some expression to get that. Okay. So the way I like to build my expression is I'm just going to copy everything that is not changing. Okay. If it's not changing, then it's always going to show up every time. Okay. So what's going to show up every time is the division, the cube roots, and the 5. All right, so just to kind of get something started here, I know that, and the minus, right? I'm going to start with I equals 1, so I need to find something that will allow, something in terms of I that will allow this to produce 2, 4, 6, and 8. Okay. Any idea what this expression could be? 2i, okay, so let's try it, let's test it out. If I plug 1 in for I get 2 times 1, which is 2. If I plug 2 in for I, 2 times 2 is 4. 3 in for I get 6. 4 in for I get 8. So it's a little bit of kind of guess and check, right? Trying to figure out, all right, I know what I value I'm working with. I know generally what my expression will look like. I just have to kind of figure out what the moving parts are. Okay. What's going to go inside the radical next to 5? Yeah, 2i again, right? It's the same pattern, right? Produces the same value. Okay, if we test this out, we should be able to get all the terms to show up. And where do we end? What should be upper bound? 4. Yeah. Okay, so 1 goes in for I. We get 2 over cube root of 2. So whatever you build, it's always good to test it out, right? Convince yourself that that you've created something that will produce every term. Okay, let me skip number 3 for now, and let's go to number 4. Okay, so number 4 says use 3 midpoint rectangles to approximate the area of the region bounded by the function, the x-axis, x equals 0 and x equals 5. So this is a problem where because you're only given the function and the a and b values and the n value, we're going to be building our width. So if we're building our width, we'll be using width equals b minus a over n. Okay. Now, if we had a table of values, we would go through the method that we did yesterday. We're going to see that on the back page. But here, we're going to build our width using this formula, okay? B minus a over n. Okay, so our a and b values are given to us, as well as our n value. A is 0, b is 5, and n equals 3. Okay, so b minus a over n. This will allow for us to create width that are the same all the way across.
Carmen Hope, please report to the main office. Carmen Hope, please report to the main office.
Okay, so now that you have your width, we're going to be building our subintervals starting at the left endpoint. So starting at 0, we're going to keep adding 5/3 until we eventually reach our destination of 5. So 0 plus 5/3 is 5/3. Plus 5/3 is 10/3. And then plus 5/3 is 15/3. Which is 5, and we've reached our endpoint, right? Okay, we could stop if it was just asking for left or right endpoint, right? Then we have the left and right endpoint of each subinterval, but it's asking for midpoint. So we have to find the midpoint of each subinterval. Right? So the way you find midpoint, you're just really just going to find the average of the two numbers, right? So that means I'm going to add the two numbers and divide it by 2, right? Dividing by 2 is the same thing as multiplying by 1/2. Okay, so off to the side here, 0 plus 5/3 is 5/3. Divided by 2 is the same thing as multiplying by 1/2. So halfway between 0 and 5/3 is 5/6. Finding the average of these two numbers, same thing as just adding the two numbers and multiplying by 1/2. So 15/3 times 1/2 is 15/6. And then adding the two numbers here, dividing by 2 or multiplying by 1/2 will get us that midpoint. So 25/3 times 1/2 is 25/6. Okay, so what we're going to do is we're going to be attaching these points to the graph. We don't have to worry about what the graph looks like. I mean, most likely it's a parabola, so maybe a graph that looks something like this. But we're just going to be attaching these points to the curve and then using that to dictate the height of each rectangle. Okay, guys, we're on page 21 in your 4.2 packet. So now we have these rectangles showing up. We're just going to be adding the areas of these rectangles. Okay? Area we know is width times height. So the width of my first rectangle, well, actually width of all my rectangles will be 5/3, right? So 5/3 is the width. The height, I want this point, and this point is coming from 5/6, so I'm going to plug 5/6 into the function. Call this f of 5/6. Right? My width component, my height component, width times height will give me the area of the first rectangle. Okay, keep going. Second rectangle, area rectangle, has a width of 5/3. But now I want to figure out the y value at 15/6 because 15/6 is the midpoint height of my second rectangle, f of 15/6. Okay. Third rectangle. And then f of 25/6. Okay, the rest will go in your calculator. You'll get to use your calculator on the quiz. We're just going to plug 5/6 in for the x and do 5/6 squared plus 3. Yeah, you can pull from that packet there. Okay, continue to just multiply and add. Okay, so that's the area approximation of the 3 rectangles added together, or area approximation under the curve using 3 midpoint rectangles. Okay, any questions here? So if you're only given the function an a and b and n value, you're going to have to go through this method of getting to the width and building your subintervals on your own. Okay. Now, next page, we have a slightly different method if you're given the table of values. Okay, if you're given a table of values,
Karen Holtz, it's working now. Please come to the main office. Karen Holtz, come to the main office.
if you're given the table of values, though, you have to understand that the width is going to be predetermined for you. So we're not going to be having to do b minus a over n. Okay, we're going to rely on the table. Okay, so we're not going to use that formula. Okay. If we do, then it's going to throw things off. You're not going to produce the approximations that we're looking for. Okay, so here's how we do it. It says use 3 left-handed rectangles with intervals indicated by the table to estimate the area between the curve and the x-axis between 0 and 7. So we're only going to go from 0 to 7. We're going to build brackets, and then we have to just make sure now every width is not going to be the same, but every width is going to span the same number of order pairs. Okay, so I only have one table here for all these problems. So if you can use a pencil just to kind of mark lightly and then erase for the other problems. So I'm going to just do that as well. So we're going to go from 0 to 7. Now, the way that you're going to build your subintervals, you're going to start at the middle of each order pair and end at the middle of the end order pair. Okay, so so as you build your subinterval, don't start at the end, start at the middle of the order pair. So we want to do 3 subintervals from 0 to 7. So it looks like I can do 3 subintervals, each seeing the same, each seeing 2 order pairs. So here's the first subinterval. We'll go from 0 to 4. Okay, notice I'm drawing from middle to middle. And every subinterval is going to share the order pair from the previous subinterval. Okay, so my second subinterval is not going to be from 6 to 7. Okay, I got to pick up where I left off and move over. Second subinterval. Okay, third subinterval from 6 to 7. Okay, good so far. So now, what we've drawn here was information that is going to give us width. Okay, we're only going to look at the top row here to get the width. And we're just going to subtract. Find the distance between these two values. So 4 minus 0 is 4. 6 minus 4 is 2. 7 minus 6 is 1. Okay, it says 3 left-handed rectangles. So that means for each subinterval, we're going to pick the left height of each subinterval. We're just going to pick whatever value we see in front of us. So for the first subinterval, the height is coming from the y value. So width times height will be 4 times 5 for the first rectangle. Second rectangle, right? That's a subinterval there. That's the order pair that the second subinterval is going to see. And we're going to pick the left endpoint y value. We're going to pick off that 3. The height is going to come from the second row. So the height is 3, width is 2. 2 times 3 will give us the area of the second rectangle. Okay, third rectangle. 7 minus 6 is 1. That's width of 1. And the height is going to be whatever that y value is showing us, 2. 1 times 2. Okay, any questions there? Pulling the width, pulling the height. Okay, let's look at part B. I'm going to erase this for my second problem. Use two middle rectangles from 0 to 10. So I need to be able to span across these order pairs, making sure that every sub-interval is going to cover the same number of order pairs. So I'm going to start at 0. Looks like I can go from 0 to 6 for one, and then from 6 to 10 for the other. Start at the middle of your order pairs. And then you're going to pick up where you left off. Okay, everybody good with that? Okay. Now you're going to ignore the middle value of your x value. Okay, that's not going to play a role right now. Okay, all you're doing right now is you're just looking to see where your bracket is pointing, and those will be the only numbers you're going to look at for the width. So 6 minus 0 will give you the width, and then 10 minus 6 will give you the width of the second rectangle. Now, when you see middle rectangles, that means you're just going to pick off literally the middle number. It may not be the true midpoint. Okay, we know that 4 is not between 0 and 6, but it is in the quote-unquote middle relative to the numbers we see there. Right. So the first subinterval, the 5 would represent the left height. The 2 would represent the height on the right, but the height in the middle, quote-unquote middle, is 3. So 6 times 3 would be the area of the first rectangle. Second rectangle, width of 4. We know 7 is not the true midpoint between 6 and 10, but for middle rectangles, we only just, whatever the middle y value is, that's what you're going to use. That's the width, 4 times 3. 18 plus 12, 30. Okay. You guys want to try part C? Pay attention to your left and right endpoint, right? You're starting at 4 and you're ending at 10. All right, any issues with part C? Okay, did we all get it? Okay. All right, let's do part D. Part D is a trapezoid. Okay. We're going to have to build each of the trapezoids separately. So here's a formula for trapezoid. It's width over 2, height 1 plus height 2. Okay, so again, we are not going to be doubling up all the middle trapezoids because the width are not the same. We're going to have to do this 3 times, okay? each trapezoid will get its own rule. That's the safest way to go, especially if you're given the table of values where the width are not the same. Okay? But we're going to draw our subinterval the same way that we did before. 3 trapezoids, 3 subintervals from 0 to 7. Okay, so we'll go from 0 to 4, 4 to 6, 6 to 7. Subtract each of the subintervals to get to your width. 4 minus 0 is 4. 6 minus 4 is 2. 7 minus 6 is 1. Okay? We just found the distance between each of those x values. Okay. Now we're just going to pay attention to where those brackets are pointing. Okay? So for the first subinterval, we're just going to use height 1 and height 2. Height 1 and height 2 will just be the ones at the ends. Okay? If your region span across multiple order pairs, then you're just going to use the order pairs at the end, or the y values at the end. So first trapezoid, width of 4, and the height 1 and height 2 will be 5 and 3. All right. First subinterval, see the bracket, it's only pointing to these 2 order pairs, so we're going to use those 2 y values. Second subinterval, width is 2, and the heights will be 3 and 2. Height 1 and height 2 will be 3 and 2. Third subinterval, width is 1, height are 2 and 3. Let's go through and clean this up. All right, any questions, table of values? Okay, so let's do a limit definition of area. Here's the formula. All right, so limit definition of area. First thing we start off with is just trying to get our a and b value and trying to insert all those pieces into our formula. Okay, so just trying to replace all the a and b values. Your a is going to be your left endpoint. Your b is going to be 2. Right. N is the number of rectangles. We are not going to have an n value, because if we had an n value like 2 or 4 or 8, then we're limiting ourselves to just an approximation. We want this to be an exact area, so we're holding on to the variable n because we're going to push the number of rectangles out to infinity. Okay, so here's my b minus a over n. Will become 2 minus a negative 1 over n, which is 3 over n. Okay. This is the width component. This whole thing is the height component. Height component, there's a lot going on here because it's finding the width and it's adding each of the subintervals, incrementing it for us, and then plugging into the function to get the height. So it's doing 3 or 4 things at once, so that's why it looks so complicated. Okay, so width is 3 over n. And my height component is f of, this is still in function notation, endpoint, or left endpoint, plus width I. Okay, are we comfortable up to that point? Any questions? So now our attention is going to focus on what to do with this function notation because we can't multiply these together. This is not in the same form. We have to get this out of function notation, okay? We have to involve this function somehow. This g of x, sorry, I used g, or I'm gonna go back and just use g of f of x just so I can get all this to be the same. But I have to rely on the 6 minus x squared, right? 6 minus x squared is going to do the job of telling me the heights of all those rectangles. So we have to somehow plug this into the function. Okay. So let's say, again, I'm going to just change this to f of x just so that I can get all the same variables here. So let's say we know f of x is 6 minus x squared. We want to reserve a spot so that the argument can plug into the right place. So I think this helps rewrite your problem and literally create an empty space where the x was. Okay, wherever you see an x is where you're going to reserve a spot for your argument. So I literally am just going to create my location with a set of parentheses and putting an empty space where the x was. Okay, so now I'm just going to insert my argument into those empty spaces. Okay. Any questions here? So now I'm going to make a substitution. I know that this f of -1 plus 3 over ni will get replaced with this piece here, right? Because we know that these are equivalent, because we see that here. All right. There's my width component, sorry, height component. So now everything is apples to apples, right? Now we can try to merge this together, but we gotta, now algebraically, we gotta go through the correct steps here. So first thing we do is we're gonna FOIL this out, get all this cleaned up. Then we can distribute the negative through, then we can combine with the 6. And then after all this is said and done, we can involve the width and get everything in terms of n. Then we can involve the summation formulas and then find a limit. Okay. All right, so here's what I'm going to do first. I'm going to take care of that binomial squared. So this will give me 1 minus 3 over ni minus 3 over ni plus 9 over n squared I squared. Okay, distribute the negative through. Combine like terms, 6 minus 1 is 5. And I'm going to start distributing the 3 over n through. Multiply the 3 over n. And now we just want every term to have a summation. And then while I'm doing that, I'm also going to start separating the parts, right? I only want either summation 1, summation I, or summation I squared, because those are the summation formulas I want to involve. Okay, I'm going to box off exactly what I'm going to be substituting. And now we're going to use the summation formulas that we're going to locate. Summation 1 becomes n. Summation I becomes n times n plus 1 over 2. And then summation I squared becomes n times n plus 1, 2n plus 1 over 6. Multiply each out, and we only care about the highest degree, right? With infinity, we only care about the highest degree. Each of the fractions have common degrees. So 15 over 1 plus 18 over 2 minus 54 over 6. So 15 over 1 is 15, 18 over 2 is 9, 54 over 6 is also a whole number, 9 as well. So 15 plus 9 minus 9 is 15. This tells us that the area of that region is exactly 15. Okay, so this afternoon, I'm going to focus on 4.1, so power rule, differential equations. Okay. And in class, we'll also hit some of these problems as well. All right, thanks, everyone. Thank you. Thank you.